In this video, we discuss diagonalization. The goal of diagonalization is to determine if a given matrix is similar to a diagonal matrix, and if it is similar, to be able to find the similarity transformation. So one of the reasons we want to look for similarities to diagonal matrices is because matrix multiplication with diagonal matrices is much faster than matrix multiplications with matrices full of non-zero entries, right? Because multiplying two diagonal matrices, you just multiply the corresponding diagonal entries. But ordinary matrix multiplication, for general matrices, you have to calculate a bunch of dot products. Okay, so we say that a square matrix is diagonalizable if it's similar to a diagonal matrix, right? So if you remember, the similarity relationship means that there's an invertible matrix P such that you calculate P inverse AP, and if this is equal to a diagonal matrix, then that says that A is diagonalizable. Right, so the similarity transformation is given by P inverse AP. Okay, so first we look at the question of how to determine if the matrix A is similar to a diagonal matrix. So there's a few theorems that describe this situation, but for these theorems I'm not going to prove it in this video because they're quite lengthy, and if you're interested, they are available in the textbook to look up. But so what we're going to do is we're going to discuss the theorems and look carefully about what they're actually saying about these matrices. Okay, so theorem 7.4 says that if two matrices are similar, then they have the same eigenvalues. Right? So in fact, similar matrices have the same characteristic polynomial. And so one thing that you can take away from this theorem is that if A is similar to a diagonal matrix, and for a diagonal matrix, right, a diagonal matrix is triangular, right? So that means that the entries on the diagonal matrix are exactly the eigenvalues. So the eigenvalues of A would be the same as the entries on the diagonal matrix if A is diagonalizable. Okay, so now let's look at the next theorem, which gives you a condition to check if a matrix is diagonalizable or not. So it says that a matrix is diagonalizable if it has n linearly, if and only if it has n linearly independent eigenvectors. So essentially what you can take from this statement is that to determine if a matrix is diagonalizable, we want to go through the process of determining the eigenvectors for A. And the diagonalizability depends on how many linearly independent eigenvectors we can find. So additionally, eigenvectors corresponding to different eigenvalues are automatically linearly independent to each other. So what that means is that if the matrix has n distinct eigenvalues, then it will have n linearly independent eigenvectors, and in this situation then then A is automatically diagonalizable. So so the possibility for it to not be diagonalizable is when it has some repeat eigenvalues, meaning that there are multiplicities that are higher than 1. Right, so in the situation where some eigenvalues have multiplicity higher than 1, then A may or may not be diagonalizable. And so the condition to check in this case is you compare the dimension of each eigenspace to the multiplicity of the corresponding eigenvalue. Right, so if the dimension of each eigenspace is the same as the multiplicity of each eigenvalue, then for every eigenvalue, then A is diagonalizable. And if the dimension of the eigenspace is less than the multiplicity, then it's not. Okay, so if you remember back to the previous section, there was a discussion on the eigenspaces for an eigenvalue. Right, so we had this inequality where the dimension of the eigenspace is always less than or equal to the multiplicity of the eigenvalue. So in the case where they're equal for all of the eigenvalues, then it's diagonalizable. But if it's less than, then it's not diagonalizable. Okay, so we can determine if a matrix is diagonalizable by comparing the multiplicity of the eigenvalues with the dimension of the corresponding eigenspace. So with that in mind, how do you actually go through with calculating the diagonalization? So again, you need to compare the multiplicity of the eigenvalues with the dimensions of the eigenspace. So the first step basically is to go through the whole process of calculating the eigenvalues using the characteristic polynomial, and then proceeding to determine the eigenspaces. So once that's done, and you know if it's diagonalizable or not, if it is diagonalizable, the next step is to form the matrix P, which allows you to calculate the similarity transformation. And this is fairly straightforward, right? Because once you have your linearly independent eigenvectors, then you can just form P by taking the eigenvectors as the columns of the matrix P. And then from there, you can just calculate the similarity transformation P inverse AP to obtain the diagonal matrix D. And as we said before, in this situation, the diagonal matrix will have the eigenvalues along the diagonal entries. And an additional thing that you get is that the order of the eigenvalues along the diagonal should be the same as the order that you list the eigenvectors as column vectors, right? So if you change the ordering of the eigenvectors along the columns, then it'll change the ordering of the eigenvalues for the matrix D. Okay, so since the first step of diagonalizing a matrix requires determining the eigenvalues and eigenvectors, it would be a good idea to review the material in section 7.1 where we discussed that. But to save time, we're going to look at previous examples where we've done this already so that we can just continue with the remaining steps. So in this example, we're asked to diagonalize this 2 by 2 matrix -3, 10, 5, 2. But this 2 by 2 matrix was the matrix we looked at in section 7.1, example 2i. Right, so this was the example that we did in section 7.1, where we've already calculated the eigenvalues and the corresponding eigenvectors. So step 1 has already been completed. Right, so step 1 was completed. In section 7.1. Right, so again, let's write them, we'll copy them over here. So lambda, the two eigenvalues were -8 and 7. And my eigenvectors, so let's call them P1 and P2, following the notation in this section. So my first eigenvector was -2, 1. And my second vector is 1, 1. And in this situation, the two eigenvalues are distinct, and so A is automatically diagonalizable. Okay, so that's step 1. Now step 2. So we need to obtain the matrix P, but then that just means I take the eigenvectors and list them as columns, right? So say -2, 1, and 1, 1. Right, so this was P1, this was P2. So I have my matrix P, and so because P is 2 by 2, it's not so difficult to obtain the inverse matrix, right? So the determinant is -2 minus 1, so you get -1 over the determinant times, and these two switch places, so 1, -2, and this becomes -1, this becomes -1. Okay, so this is -1/3, 1/3, 1/3, 2/3. Okay, so we have our matrix P, and then now we just calculate the diagonal matrix. So P inverse AP is -1/3, 1/3, 1/3, 2/3 times A, which is -3, 10, 5, 2, times P, which is -2, 1, 1, 1. Okay, so now we multiply these matrices together. So they're 2 by 2 matrices, so it's not, the multiplication isn't too bad, but to save time, I've already calculated, I've already put these matrices into the calculator, right? So this is our matrix A, and I've put matrix P in for B, right? So now I just need to calculate P inverse AP, or on the calculator, it'll be B inverse A B. Okay, so then I get our diagonal matrix with -8 and 7 on the diagonal. Okay, so this was the calculation. And so this is our matrix D, and you can notice in the diagonal entries, the first diagonal entry is -8, the next one is 7, and that's exactly our two eigenvalues, which is what we should expect, right? So that's again another way of you checking that the calculation is correct. Okay, so as we said, the ordering of the eigenvalues here depends on the order that you take the eigenvectors, right? So I can see what happens if I switch the columns here, right? So notice if we switch the order of the columns in P, right? So say I take P to be so P2 goes first, 1 1, -2 1. Okay, so I'm putting P2 first, then P1. So let's just change it here. Right, so I'm going to change my matrix B. And so this becomes 1, -2, 1 1. And so if I carry out the same calculation as before, you can see now that the order of the diagonal entries has changed places, which again is exactly what we expect. So P inverse AP now gives us this new result, right? So again, if you change the order of the eigenvectors, then the ordering of the diagonal entries of the eigenvalues here changes accordingly. Okay, so so now in this example, I'm going to try to diagonalize a 3x3 matrix. So again, I'm taking an example from the previous section, so I don't have to go through the process of getting all the eigenvalues and eigenvectors again, right? So this matrix A is from this example in section 7.1, which was already calculated, right? So we've already determined the eigenvalues as -3, 1, and 2. So it was again -3, 1, and 2. And the eigenvectors which we proceeded to calculate down here, right? So these were the eigenvectors. So the first one, -2, 1, 2. -2, 1, 2. P2 is 0, 1, 0. 3, 4, -2, 1. Okay, so step 1 again was done previously. Step 2, right? So I form my matrix P by just taking the eigenvectors as columns. So -2, 1, 2, 0, 1, 2, 0, 1, 0, then 4, -2, 1. And okay, so then now to obtain the diagonalization, right? So we just do P inverse AP. So to save time, let's just quickly enter the matrices in and calculate. That's A. Then P is, oh, that was, I put in P. Okay, so B is going to be A. Okay, so that's my A. So I've switched A and B here. Okay, so now I can calculate the diagonalization. Right, so A is my P. So I do A inverse. B is my A. And then A is my P. So I do this calculation and I get -3, 1, 2, which again is exactly what I should get as the diagonal entries from coming from the eigenvalues. Okay. And I mean, again, we already know it has to be diagonalizable, right? Because all three eigenvalues are distinct. Okay, so that's the diagonalization. And again, if you want the eigenvalues in a different order, you can just switch the order of the eigenvectors for P. Okay, so so let's look to see how we can use the diagonalization to simplify some matrix calculations, right? So again, if we know A is diagonalizable, then we have the similarity transformation. So I want to relate A to D, so I'm going to solve this equation for A in terms of D, right? So if I want to cancel out the P and the P inverse and the P, I need to multiply on the left by P, right? So then this will cancel out, and then I need to multiply on the right by P inverse, and whatever I do on one side of the equation I have to do on the other side, and they have to be in the right places, right? Because matrix multiplication is not commutative, right? So if I multiply something on the left, it has to be on the left, and if I multiply something on the right, it has to be on the right. Okay, so I multiply it like this, then this cancels and this cancels because that's just the identity. So what do I have? Right, so this gives me, this is just A on this side, and this is now P, D, P inverse. Okay, so now suppose I want to calculate the power of a matrix, right? So let's say I raise the matrix A to some power. Then, because these two things are the same, it's the same thing as raising this thing to some power, to the power k. But what does it mean to raise a matrix to a power, right? So exponents are just repeated multiplication, right? So raising something to the kth power means you multiply that thing by itself k times, right? So this thing gets multiplied by itself however many times k is, right? So there should be k factors here. Okay, so now let's look at this product here, right? So I mean, it's associative, right? Multiplication is associative, so the parentheses here are not that important, right? But notice I have P inverse times P here, right? So this cancels. Like again, I mean, the parentheses aren't important because matrix multiplication is associative, right? So I didn't write the missing factors here, but there would be another P, D, P inverse here, right? So this P inverse is also next to a P, right? So that will also cancel out. And this P has a P inverse coming right before it, right? So this will also cancel out, right? So now what does this product look like? It looks like P times D. This D is still here. This D is still here, right? So all this P inverse P will cancel out, but then there's still a bunch of D's in the middle, right? So there's still K of these D's, right? So all those D's is just D to the K. Okay, so we get that A to the K is equal to P times D to the K, P inverse. Okay, so the benefit of having an equation like this is that raising a diagonal matrix to a power is a lot easier to calculate than raising a general matrix to a power, right? So here I can just raise the diagonal entries to a power, but that's not true for a general matrix. You have to carry out the matrix multiplication, right? So so for example, let's take the previous matrix A, right? So A is this matrix here. So let me just copy this. Right, so for this matrix A, right, so I want to compare A to the K versus P times D to the K, P inverse, right? So so let's actually calculate P inverse here. I've already previously calculated it, but let's just check it again. P was my A here, right? So P inverse is this thing. Did I calculate this? No. So let's put this in. Yeah, before I had A and B in the correct thing, so don't pay attention to that. Okay, so what is P inverse? It was this thing, right? So okay, so this P written out would be this P, right? So negative 204 1 1 negative 2 201, and then d to the k. Okay, so what is d to the k? Okay, so again, raising a diagonal matrix to a power is just raising the individual entries to a power, right? So d to the k is negative 3. Okay, so let us specifically take a particular k, so like to the 5th power or something. Okay, so raised to the 5th power. Okay, so this is to the 5th power. And what are the other eigenvalues? 1 and 2, right? Okay, so 1 to the 5th, 2 to the 5th. The other entries are 0. Okay, so d to the 5th would be, so negative 3 to the 5th is, what is that? 81 times negative 3 is negative 243. This is 1. 2 to the 5th is 32. And then P inverse was this matrix here, right? So negative 0.1, 0, 0.4, 0.5, 1, 0, 0.2, 0.2. Okay, so this would be the calculation for the right side, and we want to compare it to this raised to the 5th power. Right, so I mean, this part was easy to calculate, but then you have to do 2 additional matrix multiplications, but that's not too bad, right? So for this one, to raise something to the 5th power means to multiply by itself 5 times, right? Because in general, you cannot just raise the entries to a power. That's only true for a diagonal matrix, right? Because for diagonal matrices, the diagonal entries just multiply to each other. But for a general matrix, this matrix multiplication involves a bunch of complicated dot products, right? So so you have to carry out the individual matrix multiplications. Now this one's not too bad, right? Because some of the entries are 0, but imagine that these are non-zero. If you don't optimize this matrix multiplication at all, then I mean, each individual row has 3 multiplications. Each individual row and column has 3 multiplications. There's 9 entries, right? So that's 27 individual multiplications for the entries here, just for this one, and then you have to repeat it 4 more times, right? So that's 100 something. What is that? 108 individual multiplications between the entries to calculate all the dot products, right? Whereas here there's much fewer involved, because in the end it's really only these 2 multiplications plus the exponentiation here. So the amount of individual multiplications between the entries is much fewer in this calculation versus this calculation. And as a matter of fact, I've already previously calculated this to be this result here. Okay, so we looked at some examples of how we do the diagonalization. So now let's see what can go wrong so that a matrix is not diagonalizable. Right, so let's look at this matrix A here. It's upper triangular, right? But it's not quite diagonal because there's this extra 1 located in the position here, right? So, but it's upper triangular, so the characteristic polynomial is straightforward, right? So, so if you do determinant of lambda I minus a, what does it look like? Lambda minus 1, lambda minus 1, lambda minus 2, so minus 1 here. But the determinant of a diagonal matrix is just the product of its diagonal entries. Right, so, and then this appears twice. So when you set it equal to 0, you get that you only get 2 different eigenvalues, right? So you get lambda 1 to be 1, but with multiplicity 2. And then the second eigenvalue 2 has multiplicity 1. And so you can just take the power of the factor to be the multiplicity. Right, okay, so we have our 2 eigenvalues, right? So now let's look at the eigenspaces. So for lambda 1, lambda equals 1, right? So I have to augment the 0 matrix, and then I take the eigenvalue and I plug it into lambda here, right? So 1 minus 1 is 0. So this is 0. 1 minus 2 is negative 1. And this is negative 1. Okay, so now if I row reduce this, it's fairly straightforward, right? So to turn this to 1, I multiply by minus 1. Then I can swap this row up and then multiply by minus 1. So this becomes 0, 0, 1, 0, 0, 0, 0, 0. But this is a 0. Okay, so here x1 is free. Okay, so x1 is t. And then x2 is equal to 0. x3 is equal to 0. Okay, so for the eigenspace, you get t times 1, 0, 0. But the dimension of this eigenspace is equal to 1, right? Because there's only one free variable here. So we already see that it's not diagonalizable. Okay, so from the first eigenvalue, you can already see that it's not diagonalizable. But you can find the eigenvector for lambda 2 also if you want. Right, so lambda 2 is equal to 2. So when you plug it in, what do you get? So 2 minus 1 is 1. 2 minus 2 is 0. And then I can use the second row to cancel upwards. Right, so this becomes 1, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0. So now x3 is free. x1 is equal to 0, x2 is equal to 0. So this eigenspace is t times 0, 0, 1. Okay, so dim of this one is equal to 1. Okay, but I mean, it has to be 1, right? Because when the eigenvalue has multiplicity 1, the dimension of the eigenspace is automatically 1. But we've already seen previously that from the first eigenvalue, the dimension doesn't match up, and so it's not diagonalizable.